Hello friends, let's continue our discussion on trying to quantify the response of a material when you have a system, or rather a two-dimensional system, and the condition that we impose are not confined to one direction, but it is imposed on two directions. So let me just give you the way we have constructed this particular system. We have a two-dimensional system and we have load that are operating on two directions. Py and Px are the loads that are operating on the directions x and y respectively. Now what we are trying to do is we are trying to arrive at quantify the response of a material in response to both the loading condition which are operating simultaneously. So that is what we are trying to quantify. In the previous lecture we were able to quantify that the strain along the y-axis, which is the combination of strain along the y-axis due to the load along the y-axis plus the strain along the y-axis due to the load in the x-axis. Now we were able to arrive at an expression that looked something like this, wherein we have our stress along the y-axis and we also have our stress along the x-axis, and two constants, those are the Young's modulus and the Poisson's ratio. So this is how we were able to arrive at the strain in the overall strain in the y-axis in combination or due to the combinatory load of y and combinatory load in the y and x direction. Now let us see how the strain in the x-axis will be when you have the similar combinatory load. So similar to the strain in the y-axis, the strain in the x-axis would also have two components to it. And this strain, the first component would be the strain in the x-axis because of the load in the x-axis plus the strain in the x-axis because of the load in the y-axis. Now the strain in the x-axis because of the load of the load in the similar direction, that is epsilon xx load, and the strain are all along the same direction, that is the x-axis. This can be expressed from the relation the stress by the corresponding strain is equal to the Young's modulus, and based on this relation you could express this, that is the strain in the x-axis because of the load in the x-axis, as something like this. And now in order to express the strain in the x-axis due to the load in the y-axis, that is this, we need to invoke the Poisson's ratio, and the Poisson's ratio tells us it gives us the ratio of lateral strain and the longitudinal strain, since when you consider the load along the y-axis, the epsilon xy is the change in the lateral direction or the strain in the lateral direction. The Poisson's ratio is correspondingly expressed as something like this. For the load in the y-axis, this would be the longitudinal strain and this would be the lateral strain, and from that we get our Poisson's ratio. And now based on this Poisson's ratio you can express this strain here as the negative product of Poisson's ratio and the strain in the y-axis due to the load in the y-axis. Let me write it more clearly. It will be something like this. Now we have seen, or in the previous lecture we have shown that this strain in the y-axis due to the load in the y-axis can be expressed as this. This is a description or expression that we can get from the basic understanding of the stress strain relation. And now when you use this relation or this expression for the strain in the y-axis due to the load in the y-axis, then your lateral strain in the x-axis due to the load in the y-axis will be of the form. Now we have two strains that are acting in the x-axis. One, the strain in the x-axis due to the load in the y-axis. Then we have our strain in the x-axis due to the load in the x-axis. Pardon me, I forgot the epsilon here, so there should be an epsilon here. So this would mean that we have an expression something like this. Now the overall strain in the x-axis is the combination of the strain in the x-axis due to the load in the x-axis, that is the longitudinal strain, plus the lateral strain, the strain in the x-axis because of the load in the y-axis. And now when you substitute these 1 and 2, when you substitute both these in this expression for the overall strain, then you would end up with something like, you have your stress along the x-axis minus the Poisson's ratio and the stress along the y-axis. So if you could recollect, here we have seen that the overall strain along the y-axis is of the similar form, and if I write it here, so this is how the overall strain and stress in a two-dimensional system wherein the load is operating on both the dimension of x and y is expressed. So we have a system and the load is operating in both x and y direction, and because of this load you have a change in the dimension of the system both in the x and y direction. Now we should include not only the longitudinal strain but also the lateral strain. When we do that, such a system or such a change in the system because of this sort of a loading condition, wherein we also consider not only the longitudinal strain but also the lateral strain, your expression for the overall strain in the x-axis will be something like this and y-axis will be something like this. Now, to build on that, let us consider a three-dimensional system. Let's see how difficult it is for us to consider a three-dimensional system. If you find it difficult, maybe we will we will get around the difficulties and see an approach an easier way. If it is straightforward, then we will stick to it. So at least let's attempt to build our understanding of this two-dimensional system wherein there is a two loading condition in x and y direction. Based on our understanding of that, let's build on it and consider a three-dimensional system wherein we have the loads that are applied in all the three directions. So let this be a three-dimensional system, and the references be something like this. We have already considered this to be x and this to be y and this to be z, and now the stress along the x direction is given by something like this. The y can be understood to be something like this, and this would be the stress along the z direction. I hope you are clear with at least the representation of the system here. Now what we have is, we have, instead of a two-dimensional system, we have a three-dimensional system. We have our frame of references. Based on the frame of references, we have shown the direction of the loading. We have three loading directions. The loading is applied in all the three directions. We have x, y and z loading, and we have then calculated based on the loading, based on the cross-sectional area, then we are able to translate the loading to the stress. Now let us begin by deriving a particular strain in a particular direction. So since we have already seen strain in the x and y direction in the two dimension, let's begin by considering strain in the z direction for this three-dimensional system. Now for the three-dimensional system, the strain in the z direction because of the load in the z direction. Let's try to quantify this or try to arrive at an expression for this. We want to know what is the strain in the z direction with respect to the load in the z direction. Now since both the strain and the load are in the same direction, we can go for our principal definition or principal relation between the stress and strain. That means that load in the or stress in the z direction with respect to the strain in the same direction is equal to the Young's modulus. Again, if you notice, I have not given or attributed any subscript to the Young's modulus, so that means it is isotropic in nature. We will continue with our assumption that the material that we have is it operates, or the Young's modulus of the material is same in all the direction. So we will operate under this assumption. Now based on this expression, you can write the strain along the z direction because of the stress along the same direction as something like this. So this is a similar relation we also got in the two dimension. Now let us try to understand the strain along the z direction now because of the load in the x direction. So this is what we want to do. We want to look into the strain in the z direction because of the load in the x direction. Now here you need to understand this strain is a lateral strain. This is lateral strain because it is perpendicular to the loading direction. So x is your loading direction. So x is your loading direction for our consideration of strain in the z direction for the loading in the x direction. Now we are considering a strain in the z direction for the loading condition along the x direction. So for this strain, the primary or the loading is along the x direction, and the strain is happening in a direction that is perpendicular to it. So if you can see here, the loading is happening in this direction, and the strain we are considering along the direction that is perpendicular to the loading direction. So that means this is a lateral strain. So that we need to establish first. Even though what we are considering is a three-dimensional system, since we have considered a reference or a system or a reference that is fairly perpendicular, it's perpendicular to each other, or to put it more technically, it's a Euclidean system. So you have your direction that is perpendicular to your loading direction, or the strain direction is perpendicular to your loading direction. So that means you have your the lateral strain, and the strain that you consider can be referred to as lateral strain, and it is easy for you to now relate this lateral strain to the longitudinal strain, and this relation comes from the Poisson's ratio. For that, we need to know what is the longitudinal strain for the load in the x direction. So let me repeat that. We have shown that this strain here, the strain in the z direction because of the load in the x direction, can be treated as a lateral strain. And if you want to quantify this lateral strain, you need to know what is the corresponding longitudinal strain. For the corresponding longitudinal strain for the load in the x direction is expressed as something like this. Now this longitudinal strain is along the x direction, the strain direction is x, and the load direction is also, or the load or the stress direction is also x, and therefore this can be treated as the longitudinal strain. Now the way you can relate this lateral strain and the longitudinal strain is something like this, and this would lead you to the Poisson's ratio. And now the lateral strain can be quantified as the product of Poisson's ratio and the longitudinal strain. I hope you are clear here. What we have done is we have taken a strain because of a particular loading condition or a loading direction. We have qualified the strain as, or we have characterized the strain as the lateral strain, and once we have characterized the strain as lateral strain, we found what is the corresponding longitudinal strain, and by taking their ratio we were able to relate it to the Poisson's ratio, and based on the Poisson's ratio we were able to quantify the initial strain that we were interested in, and now we were able to quantify it. Now this longitudinal strain, if you could remember, can also be further quantified from the relation that the stress and the corresponding strain is equal to the Young's modulus. So that would mean that this longitudinal strain is nothing but the ratio of stress along the direction with respect to the Young's modulus. Now ultimately what you end up with is the strain along the z direction because of the load along the x direction is equal to the negative of the Poisson's ratio and the stress along the x direction with the Young's modulus in its denominator. So what we have here is we have an expression now for the strain in the z direction because of the load in the x axis, and we have expressed that strain in relation to the stress along the x axis. Now we can try to arrive at a similar expression for the strain in the z direction for the stress that acts along the y axis. Now again, like we saw for the strain in the z axis with respect to the loading in the x axis, we then qualified it to be the lateral strain. The same can be done here. We have our strain in the z direction and the loading in the y direction, and since this z direction and the y direction are perpendicular, we can call this strain as a lateral strain. Now the longitudinal strain along the loading direction, that is the y direction, the longitudinal strain along the y direction will be of this form, and from the relation something like this, from the y version of the relation, something like this, or the relation that can be calculated in the y direction, we can express this longitudinal strain as something like this. So what we ultimately have is, we have a longitudinal strain in a particular direction, in the loading direction, and also a lateral strain in that loading direction. So now we can then quantify this longitudinal or lateral strain as, based on the Poisson's ratio or the description of the Poisson's ratio, something like this. So we saw that the Poisson's ratio is the ratio of lateral strain and the longitudinal strain with a negative sign. And now when you want to just quantify the lateral strain, then we take our longitudinal strain over here, and this is what the expression is. Now when you substitute this term or this expression here, you end up with an expression for the lateral strain with respect to the loading condition. So ultimately what we would have is an expression for the lateral strain that is related to its loading or its corresponding load. So let me write all the expressions that we have here. So we have one here, the expression for the lateral strain along the because of the load along the y-axis, and here we have derived a similar expression of the lateral strain because of the load in the x-axis, and it can be written as Poisson's ratio, the load or the stress along the x-axis with the strain in the denominator. And now we have also written, or we are yet to write the longitudinal strain in the z-axis because of the loading condition in the z-axis. This is fairly straightforward. It is nothing but the ratio of the load in the z-axis and with the Young's modulus. Now it is important to realize that all these Young's modulus are without any subscripts because we have assumed it to be isotropic. Had it not been that case, then both these Young's modulus and the Poisson's ratio would have their own subscript. Okay. Now what we now have is a longitudinal strain in the z direction because of the load in the z direction, a lateral strain in the z direction because of the load in the x direction, and a lateral strain in the z direction because of the load in the y direction. Now the overall strain in the z direction is the sum of all these three, the longitudinal strain and the two lateral strains. And now you can just express this as, by substituting all these here, you can express this as 1 by E sigma z minus. So when you substitute the expressions that you have derived here to this, now you can state that the strain in the z direction is this. You have now considered all the stress conditions that we have imposed on the material. We have included stress along the z direction, we have included stress along the x direction, we have included stress along the y direction. Now you, by encompassing or including all these stresses, what is the strain along a particular direction is quantified in this manner. Now the strain along the other directions. Now the way we have quantified the strain along the z directions by including the stresses, all the different stresses that were involved, we can also quantify the strain along the other directions, and they will be of the similar form. So I will just write it down because they will also form, they will also have the similar form, and you can, of course, if you are interested, you can just try to arrive at it. Now the strain, the overall strain along the y-axis in the 3 dimension, wherein the loads are being applied in all the 3 directions, will be of this form. Or rather y, you have your Poisson's ratio in the x and the Poisson's ratio in the z. So the easy way to remember is your strain is directly related to your stress in the particular direction. So if you have your strain in the z direction, it is directly related to your stress in that direction, and the strain due to the stresses in other direction should come through the Poisson's ratio. If you want to relate the strain in the other directions to the strain in the z direction, it is only possible if you come through the Poisson's ratio, and that is one of the important reason for learning about the Poisson's ratio. So we have written the overall strain in the y direction by relating it directly to the stress in the y direction, and also relating it to the stress in x and z direction through the Poisson's ratio. And now what the overall strain in the x direction can be written in the similar form as something like this. So what we ended up doing is, we have considered a three-dimensional system. We have applied load in all the three dimensions, and we have not only studied the longitudinal strain because of these loads, but we have also included lateral strain because of these three different loads, and we were able to calculate the strain of in the different directions because of this three-dimensional loading condition. So this is the expression for it, and as you can see, this expression involves all the loading directions or all the stresses in the different directions, and also two constants that are Young's modulus and the Poisson's ratio. So we have now derived at the expression for the strain in a three-dimensional system when there is a loading condition, when there is a load that is acting in all the three directions. Now let us consider the overall volume of such a system, how the volume changes when there is a strain, something like this. Now the volume of such system would be dependent on the length, breadth and height. So let us refer to the length, breadth and height as let us refer to the length as Lx and breadth as Ly and the height as Lz. So we have our own the dimensions for the system, and these dimensions are expressed as Lx, Ly and Lz. So this L, they all pertain to the dimension in a particular direction. You can call Lx as height, you can change the way you call it, but when I say Lx, it's the dimensions that is related to the x direction. When I say Ly, it is the dimension that is related to the y, and similar goes for the z direction. Now the overall change in the volume can be expressed in a way something like this. This is nothing but we have three different variables that govern the volume of a system. So it is a multivariant system. Now we want to see how the volume changes as these changes. So this can be expressed in something like this: change in the volume with respect to change in the dimension along the x-axis when all the other dimensions are constant, that is Ly and Lz are constant. So this is the component that shows how the volume changes when there is a change in the dimension along the x-axis and all the others are constant. Now we have to have some more terms for this. So plus you have change in the volume when you have change in the dimensions along the y axis, but the dimension along the x and the z are constant. Now similarly, we have a partial derivative of the volume with respect to the change in the dimension along the z axis. This is when you have the change in the dimension along x and y axis that are constant, that remain unchanged. So let me see if I have used the notations correctly. Okay. So what we have done is, we have expressed the change in the volume by considering a change in the one of the dimension while assuming the other two to be constant. So when I assume the Lx changes and others are constant, I can stop with this, and when I have the change in the Ly and others are constant, that will be pertaining to this term, and when I assume that the Lz changes and all the other dimensions are remain constant, and that would be contributed by this term here. So the change in the volume now comprises of three terms, and each of these terms assumes one dimension to be constant or one dimension to be varying and others to be constant. And so I have three different terms giving or expressing the change in the volume of the system. Now we have seen that when you have a linear setup, like in the earlier cases when we saw the relation between stress and strain, we saw in a linear arrangement the slope here, that is the slope here, which is nothing but the derivative of stress with respect to strain, is equal to the Young's modulus, which is nothing but the ratio of stress and strain. We saw this, and this is particularly true in a linear segment like this. We derived the strain our Young's modulus as the slope of the stress strain curve in the linear region, and we also saw that there is a relation between the stress and strain which also equates to the Young's modulus. So that means that in the linear region it is possible that this would be equal to this, particularly this is confined to the linear region. So that means you can rewrite this expression for the change in the volume as we had dou V by dou Lx. So that means V by Lx, and we have this differentiable term here that comes from here. So we have V by Lx in this term, and similarly we will be having V by Ly and this Ly term, plus we will be having V by Lz and this derivative of the Lz term. So this is possible only because we are in the linear region. And now if you take this V term here, V term out of all these individual terms, when we take V out of all these individual terms and bring this down here, what we have is dV by V and dLx by Lx plus dLy by Ly and dLz by Lz. What we have done from this step to this step is we have just taken the V from here and brought it to the denominator, and we have just moved it here. So we have dLx by Lx, dLy by Ly, dLz by Lz. So this is nothing but the strain along the x direction and the strain along the y direction and the strain along the z direction. So dV by V is nothing but change of the strain along the x direction, strain along the y direction, and the strain along the z direction. Again, this is only possible because we are restricting ourselves to the linear region. So because of this assumption alone, we are able to get this expression where the change in the volume of a material with respect to its original volume is the summation of strain in the three different directions. Now we have an expression for this. We have shown that this strain in the overall strain in the x direction, when you consider a three-dimensional system and the load is operating in all the three dimensions, the overall strain in the x direction is something like this. This we derived in the moments before we derived at this minus epsilon, which would be, all I did is I just took the epsilon or the Poisson's ratio out. So we have an expression something like this, and the overall expression or the overall strain in the y direction will be of the similar form, and the only thing that would have changed is we would relate this strain here in the y direction directly to the stress in the y direction, and we relate with the loading or the stresses along the other direction through the Poisson's ratio. So that means we have an expression something like this. And similarly, when you want to consider the overall strain along the z direction, you relate it to directly through the particular or the corresponding stress, and then you relate it to the other stresses by the Poisson's ratio. So let me check. We have x directly related, y and z related to the Poisson's ratio, y and y directly related x and z through the Poisson's ratio, z and z directly related x and y through the Poisson's ratio. Wonderful. Now let us try using this expression for the overall strain. Let us try to give an expression for change in the overall volume with respect to the initial volume. So using this description of the overall strain here, let's substitute that in here and write an expression for change in the volume with respect to the original volume. So we have 1 by this ratio, that is the reciprocal of the Young's modulus. We can take that out and you would end up with something like this, minus 2 epsilon, a plus would be here. So what we have is we have two y stresses along the y direction, two stresses along the x direction, and two stresses along the z direction, and we have our Poisson's ratio that is common, and we take that 2 out and this Poisson's ratio common. You have something like this, the summation of stresses in all the direction and the summation of stresses along the direction. So this can further be simplified as 1 by epsilon of (1 minus 2 Poisson's ratio), or further this is a way we can write it, or the way you could relate the change in the volume of a material or a three-dimensional material with respect to its volume can be expressed in this form, wherein you have considered all the different stresses and we have considered Young's modulus and the Poisson's ratio. So what we have essentially done is we have essentially related the change in the volume of a material with respect to its original volume to that of the stresses that are involved. Now, if you could recollect, this is how we related our initial stress and strain. The initial strain was nothing but change in the longitudinal length with respect to its original length. But now, what we have is, in the place of change in the longitudinal length with respect to its original length, what we now have is change in the volume with respect to its original volume. And instead of having a single stress term, we have a summation of stress term here. So now, if I rewrite it, if I write it in a way that reflects the ratio of stress minus strain, if we write it in that way, then it would be of this form. So the overall stress by dV by V, which is nothing but a volumetric strain. Instead of strain in the longitudinal direction alone, what we have seen is dV by V is a volumetric strain. And what we have done is we have brought this down here. So that would mean that this would be in the other side of the expression would be E by 1 minus 2 Poisson's ratio. So now what we have done is we have related the overall stress to the volumetric strain. We have now arrived at an expression where there is stress and strain in the elastic region, that is in the linear elastic region, are being related. So we are like in the initial cases wherein we have related the stress in the longitudinal direction to the longitudinal strain, we have now related the overall stress to the volumetric strain. And now we have seen when we relate a longitudinal stress to a longitudinal strain, we arrived at the Young's modulus. Now what we are doing is we are relating the overall stress to the volumetric strain, and here we would arrive at a constant which we can express it something like this. So we are including all the stress components and the overall change in the volumetric component or the volumetric strain. This would be equal to a constant that is nothing but E by 1 minus 2 epsilon. And this constant here, that is K, is nothing but the bulk modulus. So we have now arrived at a term called bulk modulus, which relates the overall strain that is the overall stress that is imposed on a three-dimensional system to that of the volumetric strain that the three-dimensional system experiences. So when you impose a load in a three-dimensional system in any directions that is possible, you compile all that load, and you also analyze or calculate the change in the volume that the material has experienced, and you relate it to its original volume, and you arrive at an expression for it. Now when you take the ratio for it, you are ultimately what you are doing is taking the ratio of the overall stress to the volumetric strain, like you did for longitudinal stress and longitudinal strain. You are doing it for overall stress and the volumetric strain, and that ratio would then relate to a constant called the bulk modulus, and that bulk modulus is related to the Young's modulus and the Poisson's ratio. So this is where all our consideration of adding dimensions to the specimen leads us to. So we started with a simple one-dimensional system just by considering the longitudinal change in the dimensions. Then we included, with the same longitudinal loading condition, we included the lateral strain, and that led us to Poisson's ratio, and Poisson's ratio helped us to relate two strains, that is lateral strain and the longitudinal strain. It helps us to relate these two strains, and then based on our understanding or ability to relate longitudinal and lateral strain, we then consider the system that is two-dimensional in nature and had stress or load acting on the two different directions, and we arrived at an expression for the overall strain in the particular direction. And based on that, based on our understanding of it, we then considered an actual three-dimensional system. We were able to understand or arrive at an expression for a strain that is occurring in a particular direction because of all the three loading conditions, and we were able to develop an expression for it, and we were then able to relate this expression for the strain in a particular direction to the overall change in the volume, and then relating to the volumetric strain to the overall stress, we were able to arrive at what we now call as the bulk modulus. So it is important to note that at this juncture, it is important to note that whatever we have been discussing, the discussions that we have been having so far are largely confined to the linear region or the elastic region. So be it Poisson's ratio, be it the Young's modulus, or be it the bulk modulus that we have considered so far, they all are confined to the elastic region, which is characterized by the linear relation between the stress and strain. In the subsequent lectures, let's try to look further into this elastic region alone, and then we will move into the inelastic region. So thanks for your attention so far. If you have any questions, do let me know, and please see to that that you are able to understand again the subscript of the different parameters that we have used. The other assumption that is important, that is critical to our derivation so far, is that we have assumed that the Young's modulus and the Poisson's ratio are isotropic in nature. They have the equal value in all the directions. So these are the different assumptions we have, and these are the ways we have built on it. So let us move away from, or let us dig a little bit deeper into the elastic region and move away to, move into the inelastic regions. So thank you for your attention, and let's see ourselves in the next lecture. Goodbye.